My name is Con Martin, and we're going to talk about spanning tree protocol. Now, we have to ask the question, what is spanning tree? Well, switches have some type of handicap when it comes to having loop prevention, where routers has this interesting value called time to live. And this time to live gives us the ability that every time we go from one router to another, whatever this time to live value is, we're going to take one away from it every time we move it to the next router. Once this value gets to 0, the interesting thing is the router just drops the packet and says, sorry, you have no more time to live. And that's why we call it time to live. Now, with spanning tree, however, we need spanning tree because our switches do not have this time to live mechanism. With our time to live, with routers, we are concerned with how many hops down the road will this packet be able to live. This is a looping mechanism. So if there is a routing loop, eventually that packet's going to die anyway because the time to live is going to run out. Spanning tree isn't really concerned with how many hops down the road it is. It's concerned with how to have a loop-free topology. So spanning tree is a loop prevention. So if we go into here and create this PC1 sitting here, and this PC2 sitting here, as data is coming into switch 1 from PC1, let's say it travels down this line here, comes into switch 2, well, this data can get to switch 1, PC2. That data can get to it, but it can also go back down this line, back down this switch link, which comes back into the switch. Well, why would the switch want the actual packet that it just sent out, or the frame that it just sent out? It doesn't. What we have created here simply is a loop. If I'm able to send a piece of data out of this device and be able to get that data back in, it's a loop. And we don't want loops, because loops can cause very, very havoc on our switches and on our switch environment. So what we're going to talk about is the 802.1d standard, the IEEE 802.1d. Now, you can go to Cisco's website to look this up. You can look up RFCs to get more information on how this works. But what we're going to explain is the basics of how spanning tree works. So remember when I said that the switches, all the switches in there, want to create a loop-free topology. They don't have a time to live, so they have to communicate some way, shape, or form. And that communication is done with bridge protocol data units. Now, these BPDUs are little pieces of messages that we send back and forth. Now, this is just what is in a BPDU. This is all the information, and we're going to look at this a little bit farther. But you can see we have some interesting information here. We get the bridge ID, we have the root ID, we got the root path cost, we got the port ID, we got lots of interesting information. The hello timers, the forwarding delays, and we're going to discuss all these. Now, this is how it looks just in that format. Let's really take a look at it. Here is a BPDU message. Really looking at the data here, we're going to go through each one of these and explain to you what these are. So when we talk about our root bridge election and our root port election and our designated and blocking stages, you would know what all that information is. So now, let's really pay attention to what we have here. This is the root bridge. This is information coming from the root bridge. And this thing is a BPDU packet, or a BPDU frame that's actually being sent from the root bridge. This is being sent from the root bridge, and look at the information he's going to share. He's going to share what my priority is. Now, this priority is the priority of himself. Of the root bridge, though, this is the root bridge extension ID. Here's the root bridge itself, the MAC address of the root bridge. Here's the cost value. Now, all this information here is about the root bridge. All this information here is about himself. So what is a root bridge? The root bridge is the master of all the switches. What's a bridge ID? The bridge ID is an ID of the switch. That's all it is. So this part right here is the information that I'm going to share about the root bridge. Well, notice that this information is the same. The bridge ID, or the ID of the root bridge, is this MAC address, and this is the MAC address of the switch itself. So when I send out a BPDU, I'm sharing information about the root bridge, and I'm sharing information about myself. Well, notice that the MAC addresses are identical for the root bridge and for myself, which is saying what? That I obviously am the root bridge. Okay? So this is the root bridge sending out BPDUs. Now, if we come over here on a non-root bridge port, you can see that we are sending out the same information, but look, he's sending out the information about the root bridge here. That's the MAC address of the root bridge, what kind of matches this over here, doesn't it? And here is the MAC address of myself. Now, if you're having a hard time seeing the difference here, because you're seeing 3A00, look right here. This is where it starts to get difference. All right, you got the 00 up here, but then you got the 1C and the 19. It's not the same. Where here they're identical. Now, the reason why I'm showing you this in this particular detail, because each one of these values means something, and we're going to discuss them. But the most important aspect of this part is to understand this is the information that's sharing back and forth. We also have our timers sitting down here that we're sharing with each other. So not only is a non-root bridge sharing information about himself, but he's also sharing information about the root bridge as well, the information that he knows about the root bridge. So let's see how all this works together. There's somewhat elections that we have to go through in order for something to become the root bridge. In our network topology, we can only have one root bridge. Now, all the work that we're going to be doing on one particular VLAN. Cisco does its topologies per VLAN, and the reason why they do that is because of each VLAN is its own broadcast domain. So you will have a spanning tree instance for each VLAN, but in our cases, learning the basics, we're only focused on one VLAN. So we start off with trying to find out who the root bridge is. Before anything else, we have to find out who's going to be the main man, who's going to be the root bridge. And in order to decide this, we have to figure out who has the lowest value to become the root bridge. Notice I said lowest. The question is lowest what? And that would be the lowest bid ID, or bid number, sorry. Now, when we say bid number, what does that mean? What is a bid? The bid is what we call a bridge ID. And that bridge ID is a combination of what we call priority, which is a priority is just a value, and a combination of the priority and a MAC address. We combine these two together. Now, every switch has its own MAC address. And all our priority values will start off the same. Our default value for our priorities on our Cisco devices will always be 32,768. Now, the system ID extension, notice I have a plus there. The system ID extension is nothing more than adding your VLAN number to this number here. So if I'm looking at spanning tree for VLAN 10, then my default priority will be 32,768, and my system ID extension number will be 10. So every VLAN has a system ID extension number, and whatever the VLAN number is, that's what the extension number is going to be. So for VLAN 10, I would have 32,768 plus my VLAN ID number, which in our case is going to be VLAN 1, because that's all we're going to be messing with. So if everyone has a default value of 32,768, which you can change, by the way, but if they're all booting up and they all have the same value, then the lowest MAC address of that will be the tiebreaker. So we have to understand this. If I have a switch here that is 32,768, and this one is 32,768, and this is 32,768 as well, they're all the same value. So whenever they're going through their election, what's the tiebreaker? Well, if I had this one at 32,700, which you won't be able to do, which you'll find out, which I'll mention in a second, this has a lower priority. So whoever has the lowest priority wins the contest, so to speak. It wins the election. But in our case, if everyone is the same priority, we will use the lowest MAC address. So if we had a MAC address here of, we'll say AA, and this is BB, BB, and this is CC, just to make it short, this switch up here will become the root bridge, because our bit number will be 32,768 AA. That will be our total bit number. Now, you can only change the priority number by values of 4096. The switch won't let you do it. And in fact, if you have a hard time knowing what these numbers are without getting out a calculator, all you have to do is type in any priority number. If it's wrong, the switch is going to come up and tell you what values you're allowed to use. So that's a nice little feature there. So with our priorities and our bit number, we get to decide who is the root bridge. This is our root bridge election. Now, the root bridge itself, its entire job is to pay attention to all the links in the topology. How is that possible? If this is the root bridge, now we have 3 switches here. What if we had 100? How would this switch, if this was the root bridge, be able to know what's going on with all the other switches to be able to determine who gets blocked and who doesn't? BPDUs. Now you know why I showed you that first right off the bat. These BPDUs are very crucial. It's how they communicate with each other. So we said, what is a bid? It's a combination of our priority value and our MAC address. What is a root bridge? It is the root of the spanning tree topology. Now this will make sense as we go later on, as I show you the tree when we're done. But this is the main part of our tree, because that's really what we're doing. We're closing off links to create our tree. Now, the root bridge is the focal point of the entire topology. So where you put your root bridge could be important, but for now we're just focusing on how all this works. What is a priority value? What is it? What is a priority? It's just nothing but a value of numbers that can be incremented by 4096 each time. Which means if I had a switch that had a priority of 4096, and I had this switch, can I go lower than 4096? Well, if I only can go in 4096 increments, then I can have this switch as a priority of 0. And this switch will be the root bridge, because this priority is lower than 4096. But if I have to go up to the next one, I can't just put 5,000 as the root bridge. My next value would have to be 8,192, if I'm doing that math correctly. So we can actually say 2. This will be our next increment. So that's 2, 8, 9, 1. Yes, 8192. So my next value for spanning tree would have to be 8,192. So if I put this value here and left this off and left this as 4096, then this will still be the root bridge because his value is less. His priority is less. So this is how we elect our root bridge, with BPTUs flowing around, communicating with each other, trying to find out who the root bridge is. Now this is important to know because as soon as a switch comes on, he says, hey, I'm the root bridge. So when switch 2 here, switch 3, and switch 1 come on, they all think they're the root bridge. So they start sending out information with each other, with BPTUs to each other saying, hey, I'm the root. Well, there's 2 types of BPTUs that a switch can receive. It's called superior and inferior. So if switch 1 had a lower bit number, and if that bit number had a lower value than switch 2 itself, as he's receiving a lower bit number from switch 2 coming in this direction, from switch 2's perspective, because lower is better, this will be a superior BPDU. And switch 2 will bow down and say, I'm not the root bridge. I thought I was, but I'm not. Switch 1 is. And not only will switch 2 bow down, but he'll also share that information with switch 3 saying, hey, I'm not the root. Switch 1 is. Now remember, switch 3 is also trying to be the root. And if he had a higher priority value or a higher bit number than switch 2, as that information was coming into switch 2 will see that his bit number was lower, therefore that BPU that's coming in is an inferior BPDU. I'm better, and I'm not going to change my status, according to root, switch 2. Sorry, you're not the root, I am. Because your BPDU is inferior. So with this communication back and forth, eventually they will all agree with who the root bridge is. So after our root bridge has been selected, which we will say this guy up here is the root, that part is done. Now what we have to find out is how we get to our root bridge. And when I mean how I get to our root bridge, what I mean is the best way to get to our root bridge. We have to find a best way to get there. Now, from this root bridge perspective, he's not really concerned about this aspect of it. He's the root. That aspect is done. He's not concerned with his best path to get to the root bridge. Wouldn't make any sense because he is the root bridge. Now, if we go back to our BPTUs, how do we determine if that's the root bridge? Okay? We determine that by looking at this little thing right here. This port cost, or root path cost. Let me go ahead and circle this right over here. This bad boy right here. Now remember, this is the root information. That's why we call it the root identifier in our BPDU. That's why we call it the root identifier in our BPDU messages. Notice that he says the root path cost is 0. Well, having a cost of 0 means you really didn't have to go anywhere. So if you didn't have to go anywhere to get to the root bridge, wouldn't that make sense that that's the root bridge? Because I didn't have to have a cost to get there. Now remember, the bridge information underneath here, this is the information about the switch itself. Now this is a root bridge. Of course, he's not concerned how to get to the root bridge because he is the root bridge. Here's a non-root bridge. Now notice, here's the root information, and here's his information. Notice that he knows that the bridge priority is 0, not the cost, the bridge priority. Okay, that's the priority. But notice that the cost to get to the root is what? 19. His cost to get to the root bridge is a cost of 19. It's just a value. We'll talk about those values in a second. So now we have this priority information saying, okay, here's the bridge root priority. He is the root bridge. And here's my cost to get to the root bridge. Well, if I had multiple paths to the root bridge, and I had each one of those paths are going to have its own cost, how am I going to decide what's the best path to the root bridge? The one with the lowest cost. Spanning tree uses what is called cost to make its forwarding or make his decisions of its elections and who's going to be the forwarding port, designated port, and so on and so on. So cost is nothing more than a number. Okay. So how is that number defined? How is it defined? A cost value is defined by two methods. One, the bandwidth of a link. Whatever the bandwidth on a link is, Spanning Tree will have a calculation to say, if this is a 100 megabits per second line, I'm going to have a cost of 19. That's why in that message that we saw, it was a cost of 19 because my switches have 100 megabits links. If I go under that particular interface, now remember, what's my interface? This is an interface. This is an interface. Okay, between our links are physical interfaces locally significant to those switches. The cost, if I go into one of those switches and go into one of those ports, let's say I go into this port and I change the bandwidth, it'll automatically change the cost value. Now, this makes a big difference because if this is a 100 megabits link and this is a 1 gig link, this could be a value of 4, where this could be a value of 19. Well, while I'm looking at this switch here, he's going to decide, well, in order for me to go in this direction, let's say this is a 100 gig link too, and this has a cost of 19. In order to get the root bridge, it costs me 19 to go in this direction. Hence my value of 19. If I go in this direction though, I have a value of 19 plus a value of 4, making this 23. See how that works? I'm going to add my cost up as I'm going from link to link to get to the root bridge, as I'm transiting each switch. Now, where is that value calculated? It is calculated as I'm leaving that particular port. So we have to understand this because this might be a bandwidth of 100 megabits per second, but that bandwidth value is configured here. It's configured here. Okay, this is 1 gig. This is 1 gig. And this is 100. And this is 100. So where does my value play a factor? It plays a factor as I am leaving the port. Switch 3 knows that the port is 100 megabits per second. So it knows it has a value of 19. But switch 2 over here, switch 2, remember we have BPDUs coming back and forth. So switch 2 has sent this information over to here, over to switch 3. Switch 3 looks at that BPDU and switch 2 says, oh, by the way, my cost to get to the root bridge is 4. Because as switch 4 is going out this link, he's calculating this as 4. He shares that with switch 3 over here. So when switch 3 sees that information, switch 3 says, well, my cost to get to you is what? Well, it's 19. So I'm going to take the cost that you have, speaking of switch 3, looking at switch 2, this is switch 3 that we're talking about now. Switch 3 is going to say, I'm going to look at your value of you telling me that it's 4 to get to the root bridge. And I'm going to add that value together and use 23 as my value to get to the root bridge going in this direction. So now I have two paths here, 23 and 19. Who do you think I'm going to choose? I'm going to choose the one with the lowest cost. Okay? Now this also might be a value of, we'll say it's 15. But from here, this is still a cost of 19. What happens there? Well, I have a tie. All right? So if I have a tie, at that point, I got to have some tiebreakers. Now, tiebreakers are very interesting because from this point, I have to figure out which link I'm going to choose as my path to the root bridge, my best path. That was, well, it doesn't really matter. Yeah, it was 4. We'll put this back on here. 4 and 15. So, I'm going to have a tiebreaker. What determines my tie between two links that have a cost of 19? What breaks that tie? Well, this will be the bridge that has the lowest bid number. So, because I have a cost of 19 going in this way and a cost of 19 going this way, I have to make the decision which way to go because I can't make it based on cost. So I'm going to break this tie based on the lowest bid number in this scenario. Okay? Now, if everyone has the same priority, in our case here, we're going to choose the one with the lowest MAC address. So we have two tiebreakers going on here. We have the tiebreaker of choosing who's going to be the root bridge by having the lowest MAC address because our priorities are the same. In our scenario here, this is deciding which port we're going to use to get to the root bridge based on who has, well, lowest cost first, but we need a tiebreaker. So again, it will be the one who has the lowest bid number. So because this has a lower bid number than switch 3, switch 2 will be chosen as the port to get to the root bridge. Now, with all that being said, once we decided what our port to get to the root bridge is, and that calculation is figured out, or that election is figured out, we now call that particular port the root port. The root port is the best path to get to the root bridge. And the best path is based on the lowest cost. So, back up here to our switches. This is the root. That's the root bridge. And now each one of these switches are going to determine who the root port is. Now, we had a cost of 4 here, a cost of 15, and a cost of 19. Now, obviously, with switch 4, it's very simple. I have a cost of 4 going in this direction, and a cost of 15 plus 19 going in this direction. No brainer. We're going to choose this as the root port. Switch 3, on the other hand, had a tiebreaker. Now, because of our tiebreaker, what happens then? We have to have whoever has the lowest bridge ID will win the root port election. Because this has a lower bridge ID than this one, we would choose this for the root port. Okay? But we're going to go back and make these just even links. Have this as 19, This is 19. So now we know it's very simple. This is going to be the root port. Okay? And the only link that we have left is this one, which we're going to talk about in a minute. So now we have to understand a couple things. On our root bridge, we will always have our ports on our root bridge as forwarding ports. Every other switch will always have a root port, a port that gets us closest to the root bridge, the fastest path to get to the root bridge. And each switch that's not a root bridge, a non-root bridge switch, will only have one root port per switch. One root port per switch. We only need one way to get to that root port, or that root bridge. If this link fails, guess what? Spanning Tree is going to recalculate and find himself another root port. So, in our scenario, with our root port up here, or our root bridge up here, and our root port here, and our root port here, we have this one link left. Between these switches, we need to determine which one of these ports between these two switches is going to be blocking and which one's going to be designated. Now, a designated port. What is a designated port? A designated port is a port that is forwarding traffic. Forwarding traffic. So, a root bridge will always have its ports as designated ports. They will always be forwarding traffic. You would never see a blocking port on a root bridge. The root bridge will always have designated ports. If I said root port, I'm sorry. All ports, this is another thing important to understand, all ports, if all the ports on the root bridge are going to be designated, we can put designated here, designated ports or forwarding ports. We also have to understand that with root ports, anytime you have a root port, on the other side of that root port will always be designated. Remember what the root port's what the job of a root port really is. Its job is to get you to the root bridge. Period. So as we're going from switch to switch, as we're sitting on each one of these switches, like switch 3 is going to say, I need to get to the root bridge. How do I get there? Through the root port. So imagine if we had 10 switches here with all these different connections. Well, we only need one way to get to the root bridge. And on the other side of that link, it's going to be designated. If it's blocked, guess what? It's not going anywhere. So that's why everything on the other side of your root port will be designated. Okay? Now, everything on the other side of a blocking port will be designated as well, but at the same time, what happens when something goes down that designated port and the other side is blocked? That's it. It's not going anywhere. So one side might be blocked and the other side might be designated, but it's a forwarding port to a blocking port on the other side. This is why we have one switch controlling everything to make sure that traffic does not take that direction. A switch will know that on the other side of a designated port is a blocking port. Therefore, it won't send traffic that direction. Now, a blocking port means just that. It blocks traffic. So if I had a block port sitting right here, and I block this port, no traffic will be able to leave or go in this port. Switch 3 knows about it. Switch 2 knows about it. Switch 2 will not send traffic down this direction, and if it does, who cares? It's blocked on its end. Switch 3 will not be able to get that traffic. I've eliminated my loop. Now, the one thing you have to understand, though, it might be a blocking port, but it will still accept BPDUs. It has to, because it's very crucial that these messages keep communicating with each other back and forth. So I might be blocking a port, but guess what? Take a guess. I still need to know about BPDUs. And if I don't get information on BPDUs, I'm going to think that something's going on and act accordingly. But at this point, just keep in mind that those blocking ports will be accepting BPDUs, but not be forwarding traffic or sending traffic out that port or bringing traffic in. All right? So now, we have this link sitting here, and we have to make a decision. We have to figure out which part's going to be blocking, which part's going to be forwarding. So we've gone through our root bridge election. That election is done. Switch 1 has done its job. He's the root bridge. Okay, doing our root port elections, every switch besides the root bridge has to decide what's the fastest port to get to the root bridge. And then every other link that's not a root port with non-root bridge switches has to make a decision between the links that are left behind. So we have to decide which one of these is going to be designated, which one of these is going to be blocking. We do this first. The first thing that we do this, we decide who is designated, and whatever is left is blocking. So we're trying to find out who's going to be the designated port between this link. So switch 2 and 3 are going to be communicating back and forth, and switch 2 and 3 is going to say, okay, I have this bridge ID, you have this bridge ID, I have this cost, you have this cost. And switch 2 and 3 are going to say, okay, well, whoever has the lowest cost to the root bridge wins, being the designated port. The lowest cost to the bridge. A lot of people miss this step. It's the lowest cost to the bridge first. So, if I had switch 3 had a cost of 19 and switch 2 had a cost of 10, trying to find out who's the designated port between switch 2 and 3, this link here, switch 2 wins the election because he has a lower cost to the root bridge, and he will be the designated port, and switch 3 will block its port. Now, if I have a tie where this is 19 and that's 19, now the costs to the root bridge are identical. So we need a tiebreaker. Guess who's going to be the tiebreaker? You guessed it, the lower bid ID. Lots of stuff going on. And this is how we do this. Ideally, we explain it with 3 switches. If you really want to know spanning tree really well, do 4, 5, 10 switches. Draw them out. If you have a lab, use all your switches with spanning tree. Okay, and this is the basics of how we get through the. We talked about what BPDUs are. We talked about what the root bridge election was, the root ports, the designated port, and the blocking ports. On the next one, we're going to talk about the actual timers and the port states and the stages of spanning tree for each one of those ports. So now our convergence is complete. We have our root bridge. This guy up here is the root. We do have our designated ports here. Designated ports because all our ports on our root bridge will be designated. And we have our root port sitting over here. Our root port sitting over here. And we also have our designated. And we have our blocking. Now remember, I'm either going to be a root port or a designated port. Okay, in this scenario. And if I'm not either one, I'm a blocking port. So it's kind of like saying the blocking port is whatever left over after we made our decisions on what's going to be what. Now, we need to understand now, switch 1, switch 2, and switch 3 agree upon this topology, but root bridge is the one that actually sees the topology as a whole. Now, anytime there's changes that are being made, the root bridge has to know about it. So when we look at this and say we have PC1 sitting here and PC2 sitting here, whenever PC1 needs to communicate with PC2, it needs to transit the root bridge. Now, there's a lot of misconceptions that the root port is how the traffic flows. Well, the root port is really for our BPDUs. Spanning tree needs to know how to get to the root bridge. It needs to know how we're going to send out BPDUs. And let's find out a reason why. If I have a particular switch that has a change, let's say we add another switch over here. Something's changed now. Something's happening. Now, once we go through all our elections, the interesting thing that happens is these switch ports will no longer send BPDUs. In fact, the only switch that will send BPDUs is the root bridge. Now, because of that, blocking ports are still expected, just like all the other ports are still expected to get BPDUs on them. For any given point of time, we are not receiving BPDUs on a particular port, that switch believes it has lost connection to that root bridge through that port. So the BPDUs are only being sent out after it becomes the root bridge. You can lab this by turning on the switches, doing debug commands, and looking at the debug messages. And once the root bridge is elected and everyone agrees, then only the root bridge is going to be sending out BPDUs. Now, there is a time where a switch will send out BPDUs, and that is called a topology change. So if I add the switch here, what I have done is I have added something to my topology. There's a change. Now, switch 2 knows about this change because his port link comes up. Spanning tree looks at it and says, okay, we have some type of change. So what switch 2 is going to do is it's going to send information up to his neighbor. So let's look at it from this way, because we're going to add another device here. Got another switch sitting over here. So let's say switch 4 was already plugged into switch 2. Everyone knows about it, everything's fine. But then we add switch 5. Now switch 4 knows about the topology change because this port comes up. And what's going to happen is he's going to start getting BPDUs on this port here. And now switch 4 needs to let somebody know. Who do you think switch 4 is concerned with? He's only concerned with letting who know? The root bridge. How is he going to get to the root bridge? His root port. This is one of the reasons why the root port is very important. The root port is the path to get to our bridge. So he's going to send over here what's called, over to switch 2 here, what's called a TCN message. This is the topology change notification. And he will keep sending these messages over to switch 2 until switch 2 comes back with a TCA, which is a topology change acknowledgement. At that point, switch 4 says, okay, now I know you got the actual message, I'm good to go. Switch 2 is now going to send that TCN message that he gets, he's going to send it out the root port. Now this is going to keep on happening. So if I had another switch down here, okay, this port now is notified. Switch 5 is going to send over a TCN message. He's going to keep sending it until switch 4 sends him back a topology change acknowledgement. Then switch 4 is going to do the same thing by sending over switch 2, and so on and so on. This will keep happening all the way up until we get to the root bridge. Now, once we get to the root bridge is going to acknowledge those topology changes, and he's going to send that topology change out to all of his links, to everyone else. So upstream, from router 6 perspective, router 5 is going to be sending that TCN that TCN, the topology change notification, over to switch 4, and it's going to go all the way upstream until it hits the root bridge. Then the root bridge is going to send all that traffic back downstream to all his switches. See? The root bridge is king. Now, how do we get these messages up there? That's right, BPDUs. Now, if we go back to our little message here, as you can see, right here, I have this interesting thing, topology change. Notice that this switch is saying, look, this is this is a topology change. Okay, we have the topology change flag on. Notice this one does not. It's not an acknowledgement or a topology change message. See the difference? So this is how we know when a topology change is going on. So with that being said, once the root bridge is elected and all the ports are elected, okay, remember the root bridge is the only one which sends out BPTUs. The non-root bridges will be the only ones that send BPTUs if there's a topology change. So if there's no topology changes, you won't be seeing other switches sending out BPTUs. Okay? So remember also that the switch port will send out a TCN message, a topology change message, out as root port every time. That's all he knows. I have a TCN, I need to send it out the root port. And he will keep sending them until he gets an acknowledgement from his neighbor, then he'll stop, and now it's his neighbor's turn to do the same thing. Okay? And this happens all the way up until we get to the root bridge. Then the root bridge sends it all the way back down to all the other switches. Now, the reason why I talk about this is because topology changes is a very nice thing to understand when you're dealing with spanning tree, because this shows you how important these BPTUs are. And if we lose BPTU information at somewhere in our topology, we're going to end up having problems. So BPTUs is what makes spanning tree work successfully. So now let's talk about our port roles. With our ports, we have two things we have to worry about. We have our roles and we have our states. So remember, when we have our root port sitting here, or our root bridge, sorry, and this is going to be our root port going up here. This is going to be our root port, and this is going to be designated. This is designated. This is designated. And this one's going to be blocking. Each one of these ports are going to have a particular role. Now, obviously, if it's a root port, my role will be root port. If I'm designated, it's going to be designated. Alternate means it's a blocking port. Okay? Now, that's our role now. Now we have roles and we have states. So we're focusing on the roles now. Backup is a little different. Okay? And I want you to think about backups as a means of having multiple interfaces going into a shared environment. Now, when we talk about a shared environment, what does that mean? That means somehow we are connected to a hub. So let's say that this link here is plugged into this switch. In fact, let's make it black like the other one. So we got these two links going across here. Now remember our election. We have to figure out who's going to be designated, and that's based on the lowest bid number. If I was plugged into a shared environment and had two links going over to this particular switch here, which actually, you know what? We're going to have to draw this a different way because we're going to be seeing these as switches. Let's do it this way. I got a perfect way of doing it. Let's scroll this down. I'm going to clear off all this ink. This is the root. Switch 2. And switch 3. All right, now this link doesn't exist. We're going to just knock this link out. And what we're going to have down here is a hub. And we're going to have two connections going into this hub. And we will make these black lines coming into this hub here. Now, during our election, remember that this particular switch had a MAC address of BB. This one had a MAC address of CC. What we have here now is we have two switch ports coming into a shared environment. So one of them are going to be either designated or blocking. Now, it's not going to be blocking because a blocking is our state. So the choices that we have for our roles, for our blocking states, our roles will be alternate or backup. So an alternate route means that we have an alternate way to get to the root bridge. However, a backup means something else. Now in this scenario, because we have everyone has the same priority, we are going to be choosing this as a designated port. This is a designated port because this has a lower MAC address, which breaks our tiebreaker. Now this switch here, because this is the root port, and that means the link between these is going to be what? Someone has to be designated. So here, this port here is going to be blocking, or I should say alternate. That's going to be my state. This is going to be alternate as well. Now if that's the case, I'm only going to see both of these as alternated. I will never have a backup port. And this is where a lot of people get confused. The only time I'm going to have a backup port, the definition of a backup port is when I have multiple ports that are in a shared environment, but one of those ports are designated. Now, if one of those ports are not designated, guess what? My designated side is over here. Both of these are blocking or alternate ports. Our roles will be alternate. What if I change the priority on this switch? Now, we got we'll say our priority up here is going to be 0. We're going to say the priority over here is going to be 4096. Now, if this priority is the default, which is 32,768, guess what's going to happen when they negotiate between switch 2 and 3 about who's going to be designated? Switch 3 is now going to win that battle there. And if switch 3 wins that battle, one of these ports are going to be designated. That means this one over here is going to be blocking. Now remember what I said the definition of a backup port is. That means that it can quickly switch from designated mode. Well, if they're in alternate mode, they can't, there's no way, because the designated will be over here. But since one of these are designated, now this one is going to be a backup port. So when this goes down, this will immediately transition into designated. So that's what our backup port is. So a good way to see this, to really see this behavior, it's just plug it into a hub. But you have to make sure one of these sides are designated. This switch has to win the election of being the designated side. Otherwise, you won't see a backup port. You would just see two alternate ports. Now, again, these are our roles. Okay? Let's talk about states. States are a little different, and they do relate to our roles. Because based on what our state is pretty much how our role is going to play, and vice versa. Really, depending on what our role is going to be, depends on what our state's going to be. So, our first state we need to talk about is blocking. Now, when a spanning tree port, which means this is a port that's participating in spanning tree, if the spanning tree port is in blocking state, we're not going to have any MAC address being learned. And of course, there's no traffic being sent. None whatsoever. We're not going to allow egress or ingress traffic. Now, from the blocking stage, we will transition over into the listening stage. Now, this happens when a link comes up. This happens when you do a no shut on a port. You've gone from blocking into the listening stage. During this stage, still no MAC addresses are being learned. And any stale MAC addresses are removed. And the reason why I mention this is because those stale MAC addresses can temporarily allow loops. So at that point, we want to get any MAC addresses that might be sitting on that port gone. Erase them. Get them out of there. Force them off that port. Now, also during the listening stage, we're really listening for BPDUs. I mean, if I went in and brought this port up during the listening stages, I'm really looking to see if the BPDUs that I sent out, it's coming back in on this port. I mean, that's really what I'm looking for. I'm really looking for loops. Okay, so during this stage, there's no traffic being transitioning at all. Now, the learning stage. The learning stage is very important because during this stage, we are going to be learning MAC addresses. This way, when we go into the forwarding stages, our MAC addresses will already be learned on that particular point, and we could just go right into forwarding and everything will be fine and converged. But again, during the learning stage, there's no transitioning. During the forwarding stage, when we go over from listening to forwarding, this is when MAC addresses are still being learned, because technically they've already been learned in the learning stage, but they're going to still be learning MAC addresses. If new MAC addresses come on that port, they will be learning, and now your traffic will be allowed to move. You will allow ingress traffic and egress traffic. So starting from the very beginning, we start off with going from blocking over into listening. Then we go from listening over to learning. Then we go from learning over to forwarding. Now, when we're in the listening stage, by default, this lasts for 15 seconds. When we go into the learning stage, because right when we hit the 15 seconds from listening, we go right into the learning stage. This also by default is 15 seconds. Now, when you combine the listening and learning stages together, we call it the forwarding delay. And this makes sense because we're delaying our forwarding traffic. During this time, we are delaying our traffic to be forwarded. So we call it the forwarding delay. So the forwarding delay is a combination of our listening and our learning stages. Now, what is a disabled port of spanning tree? A disabled port in spanning tree is a port that's not running spanning tree. Spanning tree is not running on that particular port. Okay? So this could be a port that's been shut down, This could be a port that doesn't have any link. Doesn't have a link because it's not getting the link from the other side. Or it's just the fact that you're not running spanning tree on the interface at all. It doesn't have a spanning tree instance. So these roles in port states, if we go back to the top of our list here, if we have a root port, what do you think that's going to be? That's going to be forwarding, isn't it? Right? So this will be a forwarding state. But the port is a role of root port. I'll designate it. Guess what? It's going to be forwarding. It has a role that's designated, but its state is forwarding. Now our alternate. What do you think our alternate is? Well, this is a port that's going to be blocking. And what do you think my backup is? Also, that's going to be blocking. So depending on what our roles are, depends on what our state's going to be. I know I said vice versa, but I mean, really, you have to have the root. You really have to have the port role in order to have it whatever state is in. I guess you can consider chicken and egg. I mean, you can't have one without the other. So I guess vice versa will work. But nonetheless, this is our port states and our port roles. So just like I was saying before about our timers, our forwarding delay sitting over here, we also have one thing called hello timers. Now, hello timers are done by the root bridge. Now, every one of these bridges here, every one of them will have a configuration on them for the timers. Now, if this bridge is the root, you can go onto any one of these switches that are non-root bridges, and you can change the timers all you want. All you want. And in fact, when you look at the configuration or look at the output, when you're verifying information, it will show you the timers have been changed. However, they don't take effect. The root bridge dictates the timers, which means you can go on these switches, change them anytime you want, but it's not going to play a factor. The root bridge, whatever timers are set on the root bridge, that's the timers that all the bridges in the topology will have, period. So if I set hello timers, which the default is 2 seconds, that means every 2 seconds the root bridge is going to be sending out BPTUs. Every 2 seconds. You can look at the debug and you can see these messages leaving out. A debug message, when you put in the debug messages, you can see these DPTUs coming out every 2 seconds. Then you change it to 5 seconds and watch the debugs come out every 5 seconds. Alright, so the hello timer is how often a BPTU will go out. Now, this is also important to know because when you put this on here for 2 seconds for the hello, that means these guys are expecting to get hellos every 2 seconds because their timers will be set to whatever the root bridge is. Now, remember what I said about the forwarding delay. The forwarding delay is a combination of the listening and the learning stage. Which means if this is 15 seconds by default and this is 15 seconds by default, giving me a total of 30 seconds, nonetheless, my forwarding delay will be a value of what? 15. So if I go in there and I change the forwarding delay to 30, that means my listening is going to be 30 seconds. My learning is going to be 30 seconds. And now your total listening and learning stage, your total forwarding delay is 60 seconds. So you got to be careful with that. So that's what our forwarding delay is. It's a collection of the listening and learning. Now, one of the problems that everyone has an issue with, the max age. When you read documentation on this, there's a good reason why a lot of people get confused. So I'm going to make it very simple. Remember when I told you, even though we're in a blocking state, doesn't really matter. The root ports and the blocking ports, they're all receiving BPDUs. It is important for this to happen. But if I have a BPDU that does not receive on a port, that switch believes he has lost communication with that port. So, going back to our example here. BPDUs are coming down. So, imagine if the BPDU stops coming in on this port. It just stops. He doesn't get any BPDUs anymore. So what happens is the switch believes that if I'm not getting BPDUs on this particular port, I have lost communication with that root bridge. I guess what he's going to do. If he believes that this interface on the other side of this interface is no longer connected to the root bridge, if he believes that, then why would he keep this as a root port? He wouldn't, because I'm not receiving BPDUs on this bad boy, so guess what? I am no longer connected to the root bridge. But this port is. So now we've transitioned this into the root port, but yet there's no reason for blocking this interface because there's no BPDUs coming in on it, so the interface stays up. And now you have a loop. All because somehow we lost communication to BPDUs. Now you can test this lab by filtering out BPDUs coming out of this port. You can say, nope, sorry, not going to do it. And you will watch this transition over to this root port here, and you would have a loop in your topology. And you would never see any blocking ports. So, the max age states that when I stop receiving BPDUs, I am going to wait for a period of time before I decide to start going through the listening and learning stages, which means I'm not going into the forwarding delay period for a period of time if I stop getting BPDUs on this particular interface. So let's think about that. The standard max age time is 20 seconds. That's the default. Now, these values can be changed, but for right now, they're the default. And where did they get changed at? They get changed at the root bridge. So now I have this root port sitting here. He stops receiving BPDUs. During a particular time of 20 seconds, that's when this port's going to wait before he transitions. So during that time, the max age says, if I stop receiving BPDUs on this interface, you're going to have to wait 20 seconds before I transition this port into the forwarding delay. So now I'm stuck. 20 seconds. Now, let's think about this. PC1's communicating. Everything's fine. Okay? No big deal. Everything's fine. Well, let's say we've lost communication from the root bridge. Okay? Let's say this link really was bad. All right? Not a down state. Just for some reason we've lost, maybe we have one-way communication. Somehow. So, he comes up here, and for some reason this traffic's being blocked. And of course, this port here, this root port, is no longer getting BPDUs. Once this happens, Now our max age clock starts. If our max age clock starts, we gotta wait 20 seconds. So at this point, this traffic at this point is now being blocked for 20 seconds. So 20 seconds finally comes up, and guess what? Now we get transitioned into the forwarding delay. So now this port is trying to be the root port, but yet we have to go through the listening and learning stages, which gives me another 30 seconds. So now this will eventually come up. I'm sorry, this will still be the root port. This is the root port, sorry about that. And this stays designated. And then my traffic is going to move from here over to here. But it's going to take 50 seconds to do so. Now, we like to use the term up to 50 seconds, but you get the idea. So this is spanning tree in a nutshell. And this is everything we cover. And now let's do a little bit of review of all the things that we've covered here. Spanning tree, what's the purpose of it? To prevent loops. Okay? In this scenario here, we've seen that if we actually have data coming out one port, it can easily come back into another. Now, one thing that we didn't discuss that we can discuss right now is what happens when we do have these type of communications with two ports, two links connected as so. Well, one of these are going to become the root bridge. Let's say he's the root. So if he's the root bridge, switch 2 is going to get what? From root 1, or from switch 1. Switch 2 is going to get superior BPDUs. So switch 2 will bow down from trying to be the root and say, okay, you are the root. Now, we have our FA00 sitting here and have FA01. Now we have what? Well, we have some decisions to make, because now we got to try to find out who's the root port. All right, so how do we find out what the root port is? Oh, the lowest cost to the root bridge. Well, I got two links going to the root bridge. Guess what? They're both 19. Now, if I wanted to manipulate one of these and make them lower, no brainer, but they're both 19. Both have a cost of 19. Now we have a tiebreaker. What's our tiebreaker? Well, the tiebreaker is the lowest, whatever switch has the lowest cost to the root bridge. Well, guess what? They both have the same cost, because this is 19, this is 19. So what's our next tiebreaker? Well, between the two links, whoever has the lowest bid will actually win to break that tie. Well, guess what? There is no other switch. There's only one. They both have the same bid. So on both of these links. So there's nothing I can do. So now what? There's an interesting thing called a port priority. Okay? Now, a port priority works like this. Every port on a switch has a priority value of 128 by default. Every port on the switch. If you have a 24-port switch, all 24 of those ports are going to have a port priority value of 128. Now, we're also going to have this period after this, and this one number, or two numbers, doesn't really matter. It's just one value, I should say. That number is going to be your port number. So if I'm sitting here on FA00, 01, because we're on a switch here, not a router, that means my port priority is going to be 128.1. If I was sitting on FA020, then it would be 128.20. Now, if this is FA00 and FA01, which, again, we're not on a router, so sorry about that. 1, 2. That means I'm going to have a port priority of 128.1, and 128.2. So who's going to win? The lowest port priority. Don't you love how everything is lowest in spanning tree? The lowest port priority. Now, in most cases, around the switching, everything else is going to be the highest. But when it comes to spanning tree, it's always going to be the lowest. So here, now, because this has a lower port priority, guess what? FAL1 becomes the root port. And this one is blocking. It's good to know this because if you have this topology sitting up like this, and you kind of got this loop going around like so, and switch 3 and switch 4, okay, and then you got like multiple links coming across, and then you got some links coming across here as well. You know, it could get kind of, a lot, so to speak. And if you really understand spanning tree, you'll be able to understand how each one of these ports work. So, port priority is nice to know. Now, you might find that your port priorities are off by 2 values. You might find that FAO1 might be 128.3 and FA21 might be 128.22. And this might throw you for a loop for a while until you realize that you have 2 gigabit Ethernet uplinks for your fiber. And this would be 128.1 and this would be 128.2, and then it'll start going to the fast Ethernet ports. All right? We also talked about how our BPDUs look, what's in our BPDU messages, which is very important because it gives us our information about our bridge priority. It gives us our MAC address of the bridge. It gives our MAC address of our cells, and it gives us our cost to the bridge. We got to see the difference between what it looks like from a root bridge perspective and a non-root bridge. We talked about what a bid was. We talked about what a root bridge was. We talked about what our priorities was. We talked about what our system ID extender was. We talked about what our root port was. We talked about what our cost was. We talked about our designated ports. We talked about our blocking ports. We talked about our root bridge election, our root port election. We talked about our TCN, which is our topology change. And we also talked about our roles and our states of our ports and our timers. So we covered pretty much everything that you need to know about basics of spanning tree. And that's how it all works. Alright, so we're going to do a little bit configurations with our devices. We have 3 switches configured. As you can see up on the screen there, we have switch 1 that's connected to switch 2 and 3, and between switch 2 and 3 we have a connection as well. We have our port numbers, FAO23 from switch 1 to switch 2, FAO21 from switch 1 to switch 3, and FAO24 between switch 2 and switch 3. So, the first command that we're going to learn is show spanning tree. Now, normally if you have multiple VLANs, it would continuously to scroll down, and you would see the instances for each VLAN. But for our simplicity, we're only going to be focusing on VLAN 1. When you look at the output of show spanning tree, there's a couple of important information. First, we have our information of what VLAN this instance is talking about. It tells us what protocol we're using. At this point, we're using IEEE, which is our standard 802.1d. In Cisco's instance, this will be per VLAN spanning tree. This tells me my root ID information. Now remember, this is the information of the root bridge, not of myself. Okay? We have our priority sitting here, which is really nice. This tells me this is the priority of the root bridge. And remember, this is the root bridge information. Whoever the root bridge is, he's going to be sharing that information with everyone. This is the MAC address of the root bridge. Now, this interesting thing here, it says this bridge is the root. Well, if this bridge is the root, that means it's telling you that, hey, you're sitting on the root bridge. It also tells us what our hello timers are. It tells us what our max age is and what our forwarding delay is. Now, below here, this bridge ID is the ID of who you are. So if this is the root bridge ID and this is the bridge ID and your information is the same, what does that tell you? Well, you're sitting on the root bridge. Now you can look at it that way, or you could just look at the fact that this says this bridge is the root. So let's go on to another switch. And let's do the same thing. Show spanning tree. And let's take a look at what we have here. Still VLAN information, which is good. Triple E, which is good. Here's our root information. And that root information stops right here. Our priority of our root is 32.769. Okay? Here is the MAC address of the root. The cost to get to the root, now normally if this was the root bridge, what would it say here? It would say this bridge is the root, but we're not the root. So there's two values we need to add in here. One is the cost, which is telling me to get to the root bridge is a cost of 19. The port that we have to get to the root to the actual root bridge is what? It tells me my port number, which is port 25. Now, it's port 23 that we're using though. You see that? But it's port number 25. Why is that? Well, if we're using FAO 23, what defines our port numbers? Our port numbers are defined by which port is actually on our board. And the reason why this is 25 instead of port number 23, because we have G001 and G002 on this switch. And this will be port 1, and this will be port 2. And FA01 will be port 3. So by the time we get down to here, you can see that the port of 25 is really port FAO23. This is very important information because now you can find out what my root port is. Really. I know what port it takes me to get to the root bridge. I got my hello timers of the root. I got my max age, and I got my forwarding delay. Now let's take a look at the bridge information. Because remember, this is the information of the root bridge. What about my information? Well, here's my priority, and here's my MAC address. So if I ever want to find out the MAC address of the switch, all I have to do is type in show spanning tree. And right there is going to give me that bridge ID's information. The MAC address is right here. Notice that the MAC address of this is different than this. You have 0019 and 001C. So these are two different MAC addresses. My hello timers of 2, 20, and 15 are sitting right here, but it learns these numbers from the root bridge. You can change these numbers and you can see the numbers are changed, but it's not going to obey to these numbers here. It obeys to these numbers up here, what the root bridge says. Below this, we have now our interfaces that are participating in spanning tree for this instance. What instance am I talking about? VLAN 1. So for VLAN 1, we have 2 ports that are participating in spanning tree. I have one of those ports that has a role of root, and it is now in the forwarding state. I have another one that is designated, has a designated role, and is also in the forwarding state. So I don't have any blocked ports here. Now, if switch 1 is the root, like we saw before, then that means what I said before was both of these should be designated, right? Here is our ports that are participating in spanning tree, and actually FAO 12 should not be in this bad boy, so we're just going to go ahead and shut that down. So as you can see, we both have a designated role of this, both these ports have a role of designated. From here, if both of these are designated, do you think that this port will be the root port and this one would be the root port on switch 2 and 3? Let's go find out. Here's switch 2. Look where my root port is. Beautiful. FAO 23 is the root port. That is my role, and of course I am 40, which makes sense. How about switch 3? FAO 21 is the root port. Beautiful. And look at FAO 24. FAO 24 is blocking. So the first thing we're going to do, now that we understand that this is blocking and this is also designating over here, what we're going to do now is we're going to manipulate who's going to be the root bridge. If I decide that switch 3 is going to be the root bridge, let's go on to here and make that change. The command will be spanning tree for VLAN 1 instance. And the command's going to be, well, there's a couple ways we can do this. One, we could change the priority, which is the first thing we're going to do. We're going to say priority. And notice that it says that it must be in increments of 496. I'm just going to hit 1. And it's going to say, sorry, it has to be increment of 4096. So we start off with 0. Our next value is 4096. Next one is 8192. Get the idea? Here is our default value. So we're just going to go 1 less than the default, which will be this one. Spanning tree, VLAN 1, priority, 28,672. And I'll scroll it up so you can see it better. And that's it. Now, let's go back up to our spanning tree and take a look at what we have. Notice that we have an alternate port and a root port. If this becomes a root, both of these ports, 21 and 24, should both change their role to designated. Oh. That was a show command there. Let's just type in 28,672. Wasn't paying attention. There we go. So do show spanning tree. Notice that we're going both of these. Notice that both of these transition over to the designated state. And look, I even have a port that's going through a listening stage. Why don't we follow that? Now it's going through the learning stage. Check that out. So it's set in the learning stage for 15 seconds. Now it's sitting in the learning stage for 15 seconds. As I keep typing in command, as you can see, now we're in the forwarding state. So things have changed now. So who now has the blocking port? Let's go over to switch 2, do show spanning tree. Show spanning tree. Don't need to do command when I'm in privileged exec mode. Now, switch 2 is the one that has the blocking port, which is FAO23 going to switch 1. So now switch 1 is the designated port. So let's go ahead and let's take this command off with the spanning tree priority. And let's take a look at our spanning tree. Let's give it a minute. While we're waiting for that, let's go over to switch 1 and see if it actually transitioned back over to being the root. Yep, it says this bridge is the root. So 2 should have lost its blocking port. There we go. Now it's listening. Now let's take a look at switch 3. And there it goes. Okay, it takes time for these BPTUs to get up there. And obviously, the longer the topology that you have, when you make a change like that, it's going to take a little bit of time to take effect. So don't freak out. So we saw, if we scroll back up here, when this was the root, switch 3, it said this bridge is the root, just like switch 1 did. And here, after we took off those changes, there we go. So that's cool. We got to see the listening and learning stages. This happens when a port comes down and comes back up, or just gets entered into the topology. So if we shut this down, do show spanning tree, FAO24 is no longer part of this spanning tree instance. This port, FAO24 now, is disabled. It's a spanning tree disabled port. So I'm going to say no shut. Immediately, 24 gets put back into the blocking. So let's go over here to FAO21. And let's say shut. Now, once we do this, we're killing the root port. Notice that our FAO24 is now going through the listening stage. Now it's going through the learning stage. See, just because it's an alternate port doesn't mean that we're not going, we just assume that it's okay just to bring it up. We still have to go through these phases. So let's do a no shut on this port. Notice this becomes the alternate port, and then our root port that's trying to be the root port goes through the listening and learning stages again. That's pretty cool how that happens, isn't it? So now, we've learned how to change the root bridge. And we can do this all day long. And play around to see what becomes the root port, what becomes the blocking port. And you can do it with multiple switches, not just 3. Now, how do we find the root bridge? And that's a good question. You're sitting here on root 3. How do I find the root bridge? Well, we know it's a cost of 19. Okay? How do we get that cost of 19? What were the 2 ways? Well, I only explained one, so we're gonna do that one first. So I'm gonna go into FAO21. Notice that it has a cost of 19, and I'm gonna change the bandwidth. And I'm gonna change the bandwidth to we'll say 4. Just 4. Now let's take a look at our spanning tree. Notice that my cost has really raised. It's a lot bigger than 19. So once we change the bandwidth, this is what happens. You immediately change the cost. Now, what if you don't want the cost to be affected by the bandwidth? Well, you can go into the interface and say spanning tree cost and the value. We'll give it a value of 55. Done. Do show spanning tree. This is the second way of manipulating your cost value of a port. And now my cost is 55. It doesn't matter now what I change my bandwidth to. I can change my bandwidth to 444. And notice my cost is the same. The interface command will override the bandwidth command. Now, the bandwidth command isn't really tied to spanning tree in that fashion. Okay, the bandwidth command is used for lots of things. It's just by default, spanning tree will use the bandwidth calculation to determine its cost. You want to hard code your cost like we did, it stays the same. Now I'm going to take this command off, and I'm going to take off my spanning tree cost command. Okay, now let's go ahead and take a look. And everything's back to normal. Now you have to understand, look how we're back into the listening stage. Let's go back and wait until we get into our forwarding stage. Almost there. Okay, we're going to go back and we're going to make this change of cost 55. Notice that when we make this cost change, notice what happened. 24 now becomes the root port. See, you got to understand why when we make these changes, spanning tree is paying attention at all times. These BPTUs in the background paying attention to everything. Any changes that are made, it's going to alert the root bridge. So before, we had 21 as the root port, which is this port going up to switch 1, which makes sense. But I gave it a higher cost. It's now 55 to go this way, from switch 3 to switch 1. To go from switch 3, 2, and 1, it's now a cost of 38. You see that? So that's why this port eventually started going through the listening stage. Not because we changed the cost, but because you alternated who was going to be the root port by the cost that you created. Now, if I was to change this port or this cost to 37 for this particular port, now remember we're on FAO 21. Notice our cost now is to get to the root bridge is 37, and we're going to be taking FAO 21. So it will transition into the root port. From here, if we make any changes that doesn't affect the root port, that's okay. We're still going through our learning stage. Labs usually take a while because you have to wait for things to transition and so on and so on. So now I'm going to change the cost to 35. Notice that this didn't change any state whatsoever. The state stayed the same because we're not making really major change that alters who the root port is. We're not transitioning a port from the root port state or into a root port state. The real question, though, is how do we find the root bridge? No matter where you are in your topology, the best way to find the root bridge is follow the root port. Okay? When we follow the root port, that's going to get us to the root bridge. I don't care if it's 1,000 switches in your topology. If you follow the root port, it'll take you to the root bridge. So how do we follow the root port? Well, we find out who the root port is on that particular switch by do show spanning tree. Then do show CDP neighbors. And this will tell us who I'm connected to. FAO 21 is the root port. FAO21 is connected to switch 1. Then we will log into switch 1, do a show spanning tree, find out what? Who's the root port? It might take us to switch 4. Then we would go into that one, do the same thing. And eventually we will get there. Again, I don't care if it takes you 1,000 times to do it. Hopefully it won't. I mean, hopefully you're not that far from the root bridge. But at the same time, this is how you will find the root bridge. If you are in a huge spanning tree topology and you don't know what a root bridge is. Now, remember what I said, after our designated ports and our root ports are decided, what's left is, whatever's left is blocking. Well, between switch 2 and switch 3, we have a decision to make. Who's going to become designated? Now, if we do look at our spanning tree, we notice that FAO24 on switch 3 is blocking. So how do we make this decision? Well, the first thing we decide is who has the lowest cost to the root bridge. So between switch 2 and switch 3, they're going to make a decision. Their decision is who's going to be designated. And switch 2 is going to say, well, I have a cost of this to the root bridge. And switch 3 is going to say, well, I have a cost of this to the root bridge. If switch 3's cost to the root bridge is lower than switch 2's cost to the root bridge, then switch 3 will become designated. But that's not the case in this because they both had the same links. Once we put this back to normal here, they both have the same cost to the root bridge. So that's when the tiebreaker is who has the lowest bid number. And if both of them have the same priority, then we're going to be looking at what? The lowest MAC address. Which the MAC address is part of our bid, right? So, do show spanning tree. We're going to copy the MAC address of this particular switch. And we're just going to paste this right here. We'll kind of move this down to kind of even up a little bit. As you can see, this bridge has a 001C. This one has a 001D. 001D, 001C. So that's why this one became designated. So I'm going to show you a way of making this a better priority. So he will become the designated port. But before I do that, I'm going to show you if I have a lower cost to the root bridge, what will happen. So I'm going to go into my interface FAO21, which I'm sure we're already in there, and I'm going to say spanning tree cost. Now my cost is going to be a value of 18 because that will give us one less lower to the root bridge. So now at this point, my root will have a cost of 18. This should be transitioning to a designated port. And look at that. There we go. All because this switch has a lower cost to the root bridge. Now let's take a look at switch 2. We're now blocking on this interface now. Okay? So that's one way of doing it. Let's look at another way of doing it. I'm going to manipulate the lower bid. So I'm going to make switch 3 the lower bid. Do show spanning tree. And we have to wait for this to transition back. Again, the BPTs have to come back, and there we go. Okay, so now we're back to alternate. So here, on this switch here, I'm going to say spanning tree. And I'm going to say root. I'm sorry, VLAN 1. And then I'm going to say root. Now, remember before, we used a priority to change a switch. And I said before that there was two ways of doing this. The first way was changing the priority to make it a higher or better root bridge. The root command allows me to do two things. One, if I set the priority It's going to drop whatever my priority is. It's going to drop it twice. If I do it, the secondary is going to drop it once based on what the bridge ID is. The primary is the same way. The primary will drop it twice if the default values of 32.768 is the root bridge. If it's not, if the root bridge is less than the priority or not the standard, it will drop it once. The first time you drop it, it will drop twice. The second time you run this command, it'll only drop it once. That's something for you to play around with. Not something to really not something really to lab with. Okay, so now spanning tree VLAN 1, and I'm gonna say root secondary. Now, what do you think was going to happen if the primary root bridge is 32.768 plus the system ID number, making it 69? What do you think is going to happen when I hit this command? Okay, look what it brought me down to, 28,672. Wasn't that the actual value? That was one less than 32.768? Absolutely. So what the root command did with the secondary is saying, okay, whatever the primary priority is, we're going to drop it one less. So that now gives me a better priority. Do show spanning tree. And notice that we've already, I don't have to even do it, it's right here. We've already transitioned into the listening stage because this has a lower priority. So we found out how to find the root bridge. Okay, we know who the root bridge is by doing a show spanning tree. That gives us the root information right up here. We found the way to get to the root bridge by following the root port. We found the way of making another port, a root port, by changing the cost, making it a worse cost or a better cost than another root port. Now remember that cost isn't just on the interface itself. It's the total collection of paths from that particular switch all the way up to the root bridge. I might change this to a value of 18, but if the total cost is still not less for this particular port, it would never transition into the root port. So you remember, your cost to get to the root bridge has to be less. From this perspective, I'm the root bridge because I changed my priority. But when I wasn't the root bridge, up here, I had a cost of 19. If you change this to, let's say this cost originally was, let's go back up here. We have 55 or 35. 35 would work. We had a cost of 35. And if I change, and you're looking at this because, well, it's 35 because I changed this port to 35. No, that's only because we're directly connected. If I change this to 55, remember the last time this was 55 and the other path was 38. And if we scroll up here, we'll be able to see that. I must have done spanning tree more than I thought. Here we go. We're starting to get to the... Oh, I lost my buffer. Shame on me. I should have gone all the way up. But nonetheless, you can rewind the video and you can actually see that aspect of it. Okay? We also saw how to manipulate the designated port by making the switch the lower priority or making that switch a lower cost to the root bridge. And he will win the designated election between a port that's not a root port. Okay? And we've solved the listening and learning stages. This is fantastic. So this is how you manipulate the switches. All these things will give you the ability to make major changes in your topology. Major changes. Don't forget about these port numbers now, because if we do have multiple links going to a particular switch, and all our tiebreakers are equal, our last tiebreaker is who has the lowest port priority. Okay? Notice that everyone has a default of 128. You can change these in increments of 16. If I try to go into this particular port and say spanning tree, port priority, sorry, and notice that it says increments of 16. If I just type in 1, it's going to say, sorry, increments of 16, but it's not going to give you the output as it would with the root bridge. So, unfortunately, you have to do the math. Everyone has a default of 128, and this is the port number that resides on the switch. FAO21 is port number 23. FAO24 is port number 26 because of the gigabit interfaces that we have. Do show IP interface brief. As you can see, this will be port 1, and this is port priority 2. I'm not priority, but port number 2. After we go through these, then we'll go back up here. This will be 3, 4, 5, 6, 7, 8. You get the idea. Okay? And that concludes our basic lab with manipulating spanning tree.